In this video, we'll introduce the final chapter of the course, Simulation and Pygame, starting with an understanding of simulation itself. So simulation is an attempt to model and imitate some real system so that it can be studied over virtual time. Right? Real-world systems are highly complex, they're difficult to study manually sometimes, so computational models attempt to distill the core mechanics of a system down to equations or algorithms that can then be studied on a machine. Now, other definitions are possible of simulation. The entire topic of simulation can fill a course or several, so consider this an introduction to simulation, not a full breadth coverage of it. Now, there's lots of applications of simulation. It's one of the places where computer science is found in pretty much every other discipline. So we can have scientific simulations of climate models and crowd behavior dynamics. We can simulate what the weather will be like tomorrow, for example. You've probably seen simulation in entertainment contexts, so video games like Roller Coaster Tycoon, for example, lets you simulate what it would be like to build and manage a theme park, or the Sims franchise lets you simulate what it would be like to have a life, a progressive career, and social skills. We can simulate things that are a little bit more valuable, like flight simulators can be used for training and simulation. So you could train pilots without ever having to put them in the air, for example. We could also use them for engineering, like testing bridge or building behaviors under certain stress conditions. We can also do civil engineering, like simulating traffic models, or business models where we're trying to estimate stock prices, or even emulation, simulating, for example, a Mac operating system on a Windows environment. These are all examples of applications of simulation. So it's, again, an application where CS reaches pretty much every other field out there. There's pros and cons to doing simulation. So in the list of pros, we have you're able to take some real-world systems and compress the time, so you can study aeons over a week or even an hour. You can also play with the system parameters to test things that couldn't possibly exist. So you could see what is it like to have a waterfall in space. So you could simulate that using these virtual things. It'd be very difficult to study that in real life. Cons, on the other hand, simulations themselves can be quite tricky to make. They have there's a lot of rules that go into creating simulations in the best practices, particularly to try and avoid biases, because a human has to create these systems, so it's entirely likely that the human's preconceived notions about those systems find their way into the models that we're designing. And of course, we'll only ever be studying an estimate of the real thing. Our simulation can never fully replicate what's happening in the real world. Right. So there's lots of reasons to want simulations and reasons to be careful when we are studying simulations as well. But let's take a look at some parts of a simulation. So the component, excuse me, the component parts of a simulation are the three things here: the model, the parameters, and the simulation loop. So the model represents or is comprised of algorithms and equations that describe the behavior of some real system. So the model focuses on trying to represent the relevant details or the mechanics of the real system while trying to abstract away all of the unnecessary, maybe superfluous parts. So for example, equations of fluid dynamics to simulate a river while ignoring things like the deer eating the grass on the shore, which may or may not be superfluous. We could study, for example, we could model agent behavior rules that they're bottom-up rules where we specify this one individual agent will do this under these conditions. It'll try and stay so far away from individual people, and then try to simulate a crowd en masse to see what happens if we take this consistent small rule and put it through maybe trying to everyone leave a theater at the same time. Right, we could also model probability distributions of customer arrivals in a simulated shop, and we'll see an example of that today, actually. Right, so that's the first part. The model is the mechanics or the representation of the real-world system. Next we have the parameters, and these are like the interface or the controls that allow us to affect the behavior of a given model. So for example, in a traffic simulation, the parameters would be things like the number of cars, the stoplight timing, the road speed limits. It's things that let us control what the outcome or what the environment that we're trying to simulate looks like. Okay. And the third part is the simulation loop. So simulation is the execution of a model through virtual time. So the simulation loop is the engine of the simulation. It continuously processes events like simulation events, so new customers arriving in our shop, or particle collisions in some atomic modeling system. But on the other hand, there's user events like mouse clicks or keystrokes, so things that our simulator needs to respond to, perhaps. Okay, so it continuously processes these events through time and optionally displays something to the screen or to a log to keep track of the current state of the model. If you're just simulating this inside a computer and you're not doing any output, then that simulation probably isn't of much value. Okay. So now, depending on how we set up these components, we get different types of simulation. There's lots of different types of simulators. So questions like, does time move continuously or in discrete time steps? Is the focus on collective entities or individual behaviors of agents? Is the system going to be deterministic, or is there some randomness in our design, right? There's lots of different questions that go into designing these simulations, and there's lots of different categories of simulations depending on how we design them. So there's many types of simulation, but they all share a common goal. We want to attempt to reproduce the behavior of a system using a computer to simulate the outcomes of some developed model. So let's see an example of this. So imagine, if you will, that you are the proprietor of a new burger restaurant and you want to know how many cashiers should you hire for your restaurant. So by studying similar restaurants, you've found a couple of details. So you know that customers are likely to arrive every 1 to 6 minutes. You'll get one new customer. And in order to process those customers, each order takes between 5 to 9 minutes to prepare and serve. So with that information, we're going to construct, or rather I've already constructed, we'll walk through a queuing simulation of this fictional burger joint. So in the provided code, you should find burgerqueue.py. It's this somewhat large piece of code, and let's walk through it together. So this is a queuing simulation of a fictional burger joint. It's stochastic, which is to say it's probability based as opposed to deterministic, would be the opposite of that. And it's discrete time. So the simulation will proceed with time as discrete steps. So it'll be a time step 1, time step 2, time step 3, as opposed to trying to represent continuous time. So each time step will represent a single minute in our simulated world. So up at the top here, we have some system parameters. In this case, just the two. So we have day end is the number of minutes that our simulation will run for. So we want to maybe simulate a shorter day of work. We can see how much that will do. Maybe it's better for us if we start at noon rather than at 10 in the morning. Okay, so that represents currently 13 hours worth of work, which I think is roughly 8 to 8, or rather 8 to 9 p.m. And then the number of cashiers. So right now we just have one cashier running the whole store. We'll play around with that parameter later on and see if that gives us different results. Now at the top of this simulator we have a number of classes that are defined. We have customer class and the cashier class. Now the customer class represents essentially timestamps as they're moving through the system. So a customer will enter the shop, we'll keep track of what time they entered the shop. They'll make an order, we'll keep track of what time they order, and they'll leave the store and we'll keep track of what time they did that as well. This will be useful for all kinds of bookkeeping information that we want to calculate at the end of this run. Okay, so the customer is mostly just storing these different timestamps. They represent almost a passive element in our simulation. And the other class here is the cashier class, and this represents the person actually processing these customers. So it's going to take one customer from the queue at a time, process their order, and then send them on their way. So we'll talk about these classes in a little bit as we go through the actual execution of the simulation loop itself. But for now, the cashier is going to keep track of the customer they're currently serving and a timestamp of when they're going to be done serving them. And then we have some methods here that let us sort of make all that work. And again, we'll talk about that when we get to the simulation loop. Okay. That method as well we'll talk about when we get to it. The report method is just a way of calculating and displaying a number of measures of interest. So again, without this the whole simulation would be kind of useless. So it's going to run the whole simulation, then run report with all of the information that we have, and we'll get some useful outputs. And then main represents our simulation loop. So at the top we have our time step starts at 0, so start counting the beginning of the day. We have a list of cashiers, so from 0 to the number of cashiers, we will add in one new cashier. So we'll create a new cashier object and attach that to our list of cashiers. We have some empty customers, so Q here is going to be the customers that have arrived to our store but haven't been served yet. And happy customers is all the customers that have left our store. Now, normally once a customer leaves the store, you just let them go, but for this simulation, we're going to hang on to them. That way we can keep track of all the information that they've built up as they come through our store. So happy customers, you can think of this as just sort of this is everybody who's left our store already. Okay. Now, new customers work by figuring out when the next customer comes in, so one customer at a time. So this function, calculate next customer, takes in a time step, the current time step, which starts off at 0. And let's go up to this function here, calculate next customer. It takes the current time and essentially just appends a random number between 1 and 6. So the next customer will show up from 1 to 6 minutes from now. And that's because of the information that we learned. The customers will arrive every 1 to 6 minutes. So this is how we're representing that in our system. So the next customer will just show up at the current time step plus that random duration. Okay. So coming back down here, that gives us this variable here, next customer. This is the time at which the next customer will arrive. So our simulation loop starts with this while loop here. It says, so long as we haven't reached the end of day, that was again a system parameter controlling how many loops to go through. Well, the first thing we'll do is we'll check, is a new customer due to arrive? So if the current time step has reached the point when we just calculated that next customer should show up, well then we're going to simulate a new customer arriving. So we'll create a customer object with the current time step and add them to the queue. So they enter the restaurant and immediately enter the queue waiting to get their burger, or waiting for their time to talk to a cashier. So passing this timestamp into customer, let me just scroll up to the top here for our customer class. We pass in a timestamp here, and this just gets stored as the time that they arrived. So self.arrived at. So they just mark the time that they came in. Again, that'll be useful later on so we can figure out, for example, how long they had to wait in the queue, the time or the difference between arrived at and ordered at, for example. All right. All the way back down here. Let's report main. Okay. So we get a new customer and we figure out, so we add this customer to the queue. Now, once this customer has arrived, we need to figure out first, when is the next customer going to arrive? So when a customer shows up, we'll figure out the next one will show up, and again, 1 to 6 minutes from now. So next customer will be updated with a new random duration, 1 to 6 minutes into the future. Okay. And some bookkeeping just so we can see our output has new customers arriving. Now, when a customer shows up, they get put into the queue. We have these cashiers sitting there waiting to handle customers. So we may have more than one cashier, so we'll ask for all the different cashiers, or for each cashier, we'll ask, is the cashier with a customer? If they're not with a customer, and there's someone in the queue, then we will serve that customer. So cashier.isWithCustomer, let's jump up here to the definition. So in the class cashier, we have isWithCustomer. And that just returns whether or not they have a customer currently stored in their active customer variable. Okay. Now, the serve customer, which happens if they're not already with one, they pull the next customer out of the queue, and that gets passed into this serve customer method. So serve customer just says store that customer. The reason being, if the customer is not in a queue, they have to be somewhere so that we don't lose track of that actual object. So while they're not in the queue, we'll put them on the cashier themselves. And then the next thing is we need to figure out when will the service finish. So we mark for the customer the current time that their order started. So customer.order at t says, just going after a customer here, says store that current time as the ordered at attribute. So they're just keeping track of the second timestamp there. That's there. And then the cashier starts their service. So service, as far as our simulation is concerned, is just an amount of time to wait. So we saw, again, from our slides, that each order should take between 5 to 9 minutes to prepare. So we'll say this service will be complete at the current time plus a random number between 5 and 9. So 5 to 9 minutes into the future. And that's something the cashier will keep track of. So they have a current customer they're serving, and now they know when that service will be complete. All right, so back down to the main loop, which is here. So for all the cashiers, if they're not currently serving someone, then serve the next customer. So pop the first customer out of the queue and pass them into that serve customer method that we just saw, along with the current time step. So cashier now has the first customer in the list. All right. And now this loop is going to keep repeating and doing all of these steps, so it's entirely possible that some time has passed and that cashier is now finished serving that customer. So for all the cashiers, let's ask, are any of them now done serving? So isDoneServing is a method inside the cashier that asks, am I with a customer, and has the time passed the time at which I will have completed helping that customer? Okay, so if the current time is greater than when the timestamp when I'll be done, then I am now done. Okay, it's coming back here. So if the cashier is done serving a customer, then what we'll do is we'll timestamp that customer. So that's the third timestamp in the customer saying service completed at. So we'll timestamp that with the current time. There we go. Oh, sorry, this is a different method. This is the method inside the cashier. Service complete does a few things. First off, we need to get the active customer out of the cashier. We want to, there's the timestamp there, customer.depart. So that's inside the customer, self.departed at t. So that stamps that third time for the customer. So now they have arrived, when their order started, and when their order finished, all time stamped. Back down to service complete. Okay, so we'll stamp the customer, tell them what time they finished, and then we'll set this cashier to idle. So we have no expected time to finish, so -1 just to be a number to say I have no number, and active customer equals none. And this is just a value that specifies that there is nothing there. So this is normally going to be an object. There's no default value for an object, kind of like a -1. So the none value works as an empty object. If you've programmed in other languages, this is equivalent to Java's null, for example. So none just means there's currently nobody being stored there. It's an empty space or an empty object. All right, and then we return that customer so that that customer can be put into our happy customers queue. There it is. So say cashier.serviceComplete. So we get the customer back from that, and we then append them to the happy customers. They are now completed. All right, so each time through this loop, we'll do all these things, check to see, is there a new customer? Are we not serving anyone? If so, serve the next one. And are we done serving? If so, then set idle. And then on the next step through, we'll get a new customer. And then one small extra step here that's very important, t plus equals 1, just a step forward in time to make sure our loop starts at 0 and eventually reaches day end. So that's the majority of the simulation right there. We're taking customers in, we're appending them to our queue, serving them when the cashiers are free and when the cashiers have completed service, then appending them to the output. So the whole trick here is just calculating when the next event should occur. So for customers arriving, that's the current time plus 1 to 6 minutes. And for cashiers serving people, that's the current time plus 5 to 9 minutes. So we just calculate what time stamp should something happen, and then we check for those somethings happening at every timestamp. So to see, did we get to the next customer? Did we finish serving a customer, which was this one here? Okay. So that's most of this simulation. Now the loop's going to keep going again and again and again until eventually we reach the point where it's done, and then we'll call this report method. So let's just jump to the definition of report here. So report is mostly just printing and calculating things. So it takes in the queue, so all the customers at the end of the day who weren't served. So as far as this simulation is concerned, maybe not super realistic, but when the day is over, after exactly 13 hours have passed, the doors lock and everybody stuck in the queue gets stuck in the queue until, I guess, the next morning. So it's all just locked in there. So we have all the information about the people who have yet to been served, as well as all our happy customers. These are the people who made it from the back of the line to the front of the line and get serviced. Right. And then we have some report information, so daily report, the amount of time simulated, the number of customers arrived and serviced, calculate the average wait time, so I have to figure out how many people are in that queue, and sum up the wait for everybody in the queue divided by the total number of customers. Calculate the average service time, so all the people that made it through the queue to the counter that actually got service, we'll figure out how many of those and what was the total service time there. And then calculate our earnings. So earnings need to be calculated in terms of how much money we're making. So we'll say every customer gave us $7 for a burger. Just to simplify it, we'll say everybody gives us the same amount. And for our wages, we'll say each cashier takes $15 in wages per hour. Sorry. All right, and we'll print out the total earnings that we made as a restaurant sans employee wages. All right, and then main just says start it all. So let's test this out. Python burgerq.py. If I hit run, it just goes spamming through a whole bunch of information. So I'm going to bring that information up here. Scroll right up to the top real quick. Okay. So it starts off, nothing happens until the left here is the current time step. So at time step 3, a new customer arrived. So the queue got filled up to 1. And now because that was the only person in the queue, the cashier was idle until this point, immediately the cashier serves that customer and the queue goes down to 0. Then at 4 minutes from then, a new customer arrives, queue goes up by 1. Another 2 minutes from then, A third customer arrives, and now our queue is up to 2. But then finally, 1 minute later, the first customer is done being served. So we'll take the next customer and our queue goes down. So we can keep track of how big the queue gets, so we can see it's increasing throughout the day. As time goes on, it gets bigger and bigger and bigger to the point where we have over 100 people waiting for their burger. So it seems like having a single cashier was not the greatest plan. We have 129 people still waiting to be served at the end of the day. In total, we served 225, so almost more than doubled that, which is pretty good, but still, number arrived was there. We served about half of the number that was arrived, so maybe not that great. The average customer wait time is 234 minutes, so that's over 3 hours long, almost 4 hours long for a burger. Maybe not the greatest. The average service time is 7. That's not going to change a lot, though, because that's a random number between 5 and 9, so that should be about there at every time. And the estimated total earnings, only $400, because we only served so few people. So what we can do with this simulation, this is the real magic of simulation, is taking this system, which seems to compute some meaningful information, and play around with the parameters a little bit. So maybe instead of having one cashier, we'll hire a second cashier and see if that lightens the burden or allows us to process more customers. So we run this again, and not going to walk through the entire thing, but we can see our queue is a lot smaller at the end of the day. That's good. It's not empty, but it's not full. 222 customers arrived, so slightly fewer, but about the same number, and we almost served all of them. We got really close. The average customer wait time is still almost an hour for a burger, so that seems maybe a bit much for a burger, but we made almost double the money, so that's pretty good. So let's see what would happen then if we ran this with 3 cashiers. And since this is random, we probably should run it a few times, so set it back to 2, sorry. And run it a few times just to see if that's consistent values. So 961, 926, 968. We're getting roughly $950 each time, so somewhere in that range seems to be appropriate. We can't take one of those values as the be-all, end-all number, but running that over maybe 30 times, we can get a statistical average and see that, in general, this is what the simulation says. Okay, so let's try now running it with one more cashier, see if we can't make that number get a little bit bigger. So not much more. We got 976 that time. We can see our customers in the queue has gone to 0. And if I scroll up through this, let me just make this bigger again. If I scroll up through this, we can see, okay, well, these cashiers were basically just fighting for work to do, right? A new customer arrived the very first minute and was immediately serviced. Another customer arrived and was immediately serviced. Another customer arrived, was immediately serviced. The fourth customer arrived, and then the first one was done. So it happened pretty quick. The queue went back down to 0, and it stayed pretty close to 0 for most of the day. I think there was one spot I saw while we were scrolling where it went up to, 3, I think, was our maximum queue about halfway through the day. One of them must have been taking a lunch minute. But as we can see, with 3 cashiers, this is maybe a bit overkill. We made a little bit more money, so we kept our queue happy. Our average customer wait time for a burger is half a minute, so that's really good. Sorry, not for the burger, that's just for the queue. But if we run this a few times, 983, over 1,000, 941, over 1,000. So we can see we are making a bit more money this way, an extra, let's say, $50, but our customers are happy, which means we're going to have more repeat customers this way. So maybe having that third cashier is better. Now, this obviously is not a super realistic simulation. We don't include anything about taking breaks. These cashiers, all 3 of them, worked from the opening of the store till the closing of the store without ever going to the bathroom or having lunch. So I imagine probably not the greatest working conditions. So a more realistic simulation that maybe involves having shift work or taking breaks, that could also be employed to maybe get more accurate numbers before we actually construct our burger joint. But that gives you the idea of what a simulator can do. So we can figure out, based on several different runs, what sort of values we want. In this case, how many cashiers we want for our burger joint. So it's worth noting here, there's no new programming concepts here. It's just a new application of all the stuff that we've already learned. So simulation's just another kind of programming. There's also lots of variety in how simulation systems work. This one's all text-based, for example. We could have a lot more enjoyment, perhaps, if we used graphical outputs. They tend to be more fun. So in the next video, we'll take a look at Pygame to do just that.